Hi everyone, thanks for joining today's Microsoft Virtual Academy. Today we're going to be exploring computational thinking. I'm not alone in studio today, with me is Namusa. Hi Namusa.
Hi Megan.
Thanks for joining me to tell us about computational thinking. Can you give us a bit of background about yourself and what work you do with relation to technology and getting teachers and learners using computers?
Okay, I'm Nomusa Keninda from the Department of Education in Mpumalanga. I was a teacher for 10 years, since 1994 to 2003 in Emalahleni. I was teaching grade 9s to 12 geography. I matriculated at Bonginsimbi Comprehensive School, then moved to University of Limpopo. By then it was called University of the North, that is Teflop campus, where I graduated as a teacher.
So Namusa, both you and I used to be teachers, even although we're no longer in the classroom. But I can't remember when I was actually teaching that there was even this term computational thinking. Well, was it a term that you came across in your studies?
It was not there, but all what we know that what we're doing was computational thinking.
Yes. So I had that same realization myself, that even if we weren't using this terminology, abstraction, computational thinking, decomposition, even if we weren't using that terminology back when we were teachers, those were concepts and skills that we were developing all the time amongst our students.
Yes. Megan, remember I'm coming from geography background where I taught most of my learners the development, the identification of rocks, you know, the sedimentary rocks, the igneous rock, morphological rocks. So all these things, when I started teaching them about a particular rock, you will put all the characteristics of computational thinking.
So what you were doing with identifying types of rocks was really an exercise of pattern recognition. You would know these are the characteristics of igneous rocks, and then when you have a new sample, you would think, well, does this fit in with the pattern?
Yeah, I remember going out with the learners on an excursion, and then we were picking up the rocks. They will tell you, hey, Mem said, this is sedimentary rock because these are the layers. It's being embedded in layers of small rocks. So you can see that these learners did understand the concept in the classroom. Now they are seeing it in the field.
Okay.
Yes.
So I'm really hoping that by the end of today's webinar, that teachers will realize that computational thinking is not some new scary concept. It's actually something that good teachers have been doing all along anyway, and it's something that definitely can be embedded into teaching whatever concepts you're teaching anyway.
Yes, in every subject, like I was saying, geography, you can also do it when you do a life cycle of a locust. Let me put it that way. So in other words, all the teachers that are presenting, the computational thinking is you cannot single out, but really teachers are doing it.
Okay, for sure. And across the curriculum, whether they're life science teachers, geography teachers like you used to be, maths or science teachers, or perhaps IT teachers, even though computational thinking has the word computational in it and people think, oh, then it must have something to do with computers. It's actually something that can be taught across the curriculum.
It's like you think, but you think like a computer.
Exactly.
With a speed, yes. What must I do with this problem? Where do I start? How do I put things together? How do I prioritize to solve this problem?
So I really like how you're defining computational thinking as thinking like a computer, because computational thinking really involves thinking about something in a structured, orderly manner. And if children learn these skills, if they're confronted by, a maths brain teaser that they haven't encountered before, or some sort of science problem where they haven't done that experiment before, if they know the skills of computational thinking, instead of being overwhelmed or sort of thinking, oh, we've never done this before, they'll be able to tackle that project or that question like a computer, thinking about it in a structured, orderly way. How can I break this down into steps? What part of this information can I ignore and focus just on what I need to be able to solve the problem? So we've already probably done it, but let's define computational thinking. How would you sum up the term computational thinking?
It's like when you are presented with a problem, you need to figure out first how big is the problem and what can you do to solve it. All the approaches that you put inside the thinking. That is computational thinking to me.
Okay,
yeah.
So computational thinking is a little bit like mathematical thinking or scientific thinking, but it's a little bit different because it can be applied across learning areas or across subjects. It's not confined to maths and science only. And it's not something that you need a computer to do, but it certainly is something that can help you leverage the power of computing. You know, if you've got a checklist or you know, a set of sort of strict instructions, you can code something to behave in a certain way. If somebody answers this, then you present them with these questions. Then of those questions, if they answer A, you present them with, you know, these next things. If they answer B, you present them with something else. So you can definitely leverage computational thinking using a computer, but you don't need a computer to sort of think computationally.
I think you can bring that example of making a sandwich. I think it is a relevant example, just to bring it to a general format so that the teachers can follow what we are talking about when we are talking about computational thinking on the things that they do every day.
Yeah, so just like we don't want teachers to get overwhelmed with the concept of computational thinking, we don't want learners to be overwhelmed either. So it's a very good idea, as you're suggesting, to bring it back to something that they do every day, like making a sandwich. So if you had to break down the process of making a sandwich into a series of structured steps, what would some of those steps be?
In other words, you need to identify the different parts that will make the sandwich. Identify them, whether they are there, and then you start making a sandwich. You bring the bread first. Of course, you need to bring the bread first. What do you need a spread on top, and then you can bring it the spread.
So you'd maybe start off, you must have some ingredients. Yes. So you'd need the bread, you'd need the spread, so maybe some margarine or some butter. Maybe you're going to put something like some cheese on your sandwich, and a nice filling. So you'd start with the ingredients, and then you'd maybe have some steps. So slice the bread. What would be the next step?
Along the way, even if you follow the step, along the way you need to give it to you need to give it to a priority. What do you really need in the sandwich? What will you really need to taste better in that particular sandwich?
Okay, so what are the minimum requirements for something to be considered a sandwich? Or
it will be all upon you. That is why we say computational thinking. It's about also bringing a priority in every situation that you want. Like, let's take the weather pattern in Cape Town. So there are all problems around shortage of water, but what is the real priority to solve the problem?
Okay, so that's going to be sort of thinking about something in terms of abstraction. So we'll get to that in a minute, but let's first just talk about the four components of computational thinking. So 4 different sort of types of thinking have been identified, and we'll go through each of these in a bit of detail, and we'll give you some examples of each. But in short, they are decomposition, pattern recognition, abstraction, and algorithmic thinking. So the first one that we're going to talk about is decomposition, and we've already done that a bit with talking about
Breaking down.
how you make a sandwich.
Yes.
Because decomposition is really breaking something up into smaller pieces. So without getting sort of overwhelmed or thinking it's too difficult, if you're going to do something, how can you break it down into step-by-step instructions? They say, how do you eat an elephant?
Yes.
One bite at a time.
Yes.
How do you solve a problem? One little piece at a time. So something that's good for decomposition is sort of breaking something up into steps, following a recipe, things like making a sandwich that we talked about. We've got an example on the screen about how you make breakfast. And breakfast might consist of, making toast and making tea. So each of those two things, making the toast and making the tea, would be two separate sub-processes of making breakfast. To make toast, you'd need to slice the bread, then you'd need to toast the bread, then you'd butter the toast, then maybe you could add some jam if you wanted. But that's how you'd make toast. To make tea, you'd need to boil the water, brew the tea, put the boiling water on top of the tea bag. Then you could add some milk, maybe some sugar if you like your tea sweet. But that would be like a simple process of decomposing or, breaking down the process of making breakfast.
But Megan, were you taught how to make a tea? Or do you look at what people are doing and then you also copy it?
I assume when I was little, my mom must have sort of shown me, but I think I also sort of picked it up from watching her make many cups of tea. So sometimes it's about being able to observe a pattern so that you can then replicate it. And sometimes it's about, trying to document the steps so that you've got them sort of handy to try and do something again yourself.
Okay. I'm just thinking that it's also coming alive. Even if you are not really taught how to make that tea, you cannot do the tea as you were taught, but you will follow a certain structure. Like you will also prioritize what quantity of sugar do you need in that particular tea.
Yeah, no, exactly. And the thing is, and where it's quite fun to actually take a set of instructions and get learners to sort of document the instructions and then get a classmate to try and carry out those instructions exactly as they say them, because it's amazing what people just leave out. So even something as simple as making tea, if you don't tell them to boil the water, then whoever's following the instructions could just take cold water out of a kettle and pour it on the tea bag. It's a silly thing to do, but it shows this is how computational thinking works. If you were to give these instructions to a computer or to a machine and didn't tell them to first boil the water, they wouldn't know to do that. For things like adding the sugar, if you don't say specifically in your instructions add 1 teaspoon of sugar, somebody could take the whole sugar bowl and tip it into the cup of tea. So those would be sort of fun, sort of silly examples, but they would really help a teacher to illustrate how important it is to be very sort of precise and clear in your directions or your instructions.
Yes.
So decomposition is useful for a number of things. It can help you determine unknowns that might arise in the process. So things like the simple example we had of making breakfast, maybe just tea and toast is fine. Maybe somebody might not want jam or on their toast, and somebody might not want sugar in their tea. So those could become optional extras that you would need to find out from the person who you were making breakfast for, if they wanted something on their bread or some sugar or milk in their tea. It's also useful for identifying key smaller components that lead to the next part of the problem. So I'm thinking here of an example from English, from language. I used to be a high school English teacher, and if you take something like a Shakespearean play, it often seems very sort of overwhelming or complex for learners to understand, particularly if English is not their first language. But if you do some decomposition, if you break that complex Shakespearean play down into acts or into main events, and then this character sort of behaved in this way, which led to the next character's action, it helps the learners to make sense of something that's very complex by breaking it down into smaller chunks.
Yes.
Okay, and it helps them to then understand the bigger picture, because they're looking at each component in turn, and how one component maybe leads to the next component.
Yes.
So
that's decomposition.
That's decomposition, right. So now we're moving on to pattern recognition. So pattern recognition is all about recognizing similarities and differences. As a former geography teacher, can you think of examples of where you could integrate pattern recognition into the curriculum?
Yes, let's talk about the recent incident that is happening in Cape Town, Western Cape. You could see that there is a change of weather pattern there. They almost receive rain during winter season, but now it has already changed. They just received rainfall now in January. And that is one of the examples that we can pick it up, that for a problem to be solved, you need to recognize the pattern of that problem.
So you need to be aware of what typically takes place, and then has something happened that's abnormal, that sort of doesn't quite fit in with the pattern, and what problems that's caused.
Yeah, I think it's a good example. In fact, all over South Africa, we kind of receiving weather patterns that are not were not there in the past. I remember recently we had a tropical cyclone Dineo around Mpumalanga, and we were overwhelmed. Where does this phenomenon coming from?
Okay.
Yes.
So students need to be able to know what's typical, what the usual pattern is, and then what's standing out that's strange. You've given a couple of nice examples from geography, but it's something that maths teachers use all the time. Students need to know these are odd numbers, these are even numbers, these are prime factors, because if you know what the pattern is and what the characteristics of, say, prime numbers are, then you're able to figure out if something is a prime number or isn't a prime number.
And we are able to group things that go accordingly. Or if there are odd numbers, you need to group them, odd numbers, even numbers, like that.
Absolutely. And a life sciences teacher would also use pattern recognition, maybe in terms of classifying different types of animals or different types of insects. If something's got 6 legs, it would be an insect, but if it's got 8 legs, it's not. And once you're able to determine patterns, you then are able to, draw conclusions about which type of species something is.
Yeah.
Okay, so that's pattern recognition.
Yes.
Another type of computational thinking is abstraction. And abstraction is really about clearing out the clutter and ignoring things that are not pertinent or important to your problem, and focusing your attention just on the problem. Can you think of an example of where a teacher might use abstraction as part of a topic he or she was teaching?
I'm thinking of a teacher who's presenting a lesson on solar system. When you look around, there are a lot of things that are in the solar system: the stars, the sun, the moon, the planets. But if I don't want to deal with the stars, I can completely ignore the stars and focus on the Earth.
For sure, for
Yes.
sure. So it's about narrowing your focus and then focusing quite clearly on that thing. So like the solar system example, you might want to then say we're only going to be dealing with planets, and you could then give each group of learners a specific planet that they need to investigate.
Yes.
So they'll then abstract even further and just look at one planet and could then share and compare their findings at the end of the lesson.
Yes, even in that particular planet, you still have to trim it down to your priority. What is it that you want to investigate on the Earth? Do you want to investigate people, or you want to investigate the structure of the Earth, or the landscape of the Earth? So it's upon your priorities. What is it that you want to deal with?
Yeah, and to rather do a sort of focused job on looking at just a couple of aspects than trying to look at everything and not really covering anything in any detail.
And I like the example that you gave it earlier, that if I'm looking for a pair of black shoes, I'm not going to go to the techies and what. I'm going to focus directly to the pair of shoes and then just take those black shoes.
Yeah, it's about getting rid of the clutter. I just want to talk the viewers through sort of one of the pictures that we've got on the screen. It shows a couple of bookshelves, A, B, C, and D. And in the puzzle, people were asked to look for the bookshelf that didn't have any rectangular objects next to each other or any round objects next to a rectangular object. So to solve this puzzle, you would only be looking for two types of objects. What would those be?
The rectangular?
The rectangular ones and the round ones?
And the round ones, yes.
So the heart-shaped thing, the triangular-shaped thing, that would kind of be neither here nor there. What would be important would be rectangles must not be next to rectangles, and round things mustn't be next to rectangles.
Yes.
So A wouldn't work because those books are all rectangular shapes and they're next to each other. B wouldn't work because it's got a round thing next to a rectangle. C also wouldn't work because again it's got a round thing next to a rectangle.
Yes.
And D, that's our lucky one.
I think it's the answer.
D is it, because the rectangles and the round things all have other shapes in between them. So that involves sort of narrowing your focus and looking just at what the question asks. It's not asking, is this bookshelf from a girl's room or a boy's room? What's the trophy for?
The length
yeah.
of it, no.
And often those maths brain teasers will sort of start off by saying, this child plays soccer and this one plays tennis. But actually that information is superfluous to solving the problem. It's just there to distract you, and you need to ignore it and focus on the problem.
Yes.
Okay, so that's one aspect of computational thinking. But the next one that we're going to talk about is algorithmic thinking.
Yes.
Now that sounds very high tech, but it's not really.
What is for maths people? No.
So how what would you say algorithmic thinking is all about in simple terms?
To me, it's about sequencing. Where do you start? You start from the lowest order until to the highest order. Or you start from the highest order to the sequence of bring the problem down.
Okay.
Yes.
Or creating a very simple sort of flow chart. If it's yes, you go this way. If it's no, you go that way.
Yes.
So, Namusa, I don't know about you, but I've had to phone the sort of help desk of my internet service provider company more than once. And I get the feeling that they are following a flow chart or actually using some algorithmic thinking. How does algorithmic thinking work in terms of troubleshooting?
Like, for example, if you want to know whether this plug fits to that plug so that the whole new environment is created. You do that. When you troubleshoot, like you troubleshoot a computer, you see wires lying around, you see the monitor is there, the computer, the keyboard is there. How do you put it together so that they now resemble a computer and it's working?
Okay.
So to me, that thinking is about putting each part together to form a whole.
Okay,
Yes.
and working out which plug fits in which socket.
Yes.
And you can't make them fit.
No.
You have to find,
The
you know,
fitting.
yes, that this one that has 2 pins goes into that hole, and that's how you connect this monitor with this sort of keyboard or CPU. And when you phone a call center and say, you know, my internet's not working or my computer's not working, often they'll walk you through a series of step-by-step questions. They will say, you know, is it plugged in? Which might seem like quite an obvious thing to check, but maybe it's something somebody hasn't realized. So if you say, yes, it's plugged in, they'll maybe say, well, is it turned on? Okay, it's turned on. You know, if your modem won't connect to the internet, they'll often advise you to turn it off, leave it for a minute, and turn it back on. And sometimes that solves the problem. If it doesn't, they'll have the next step in their troubleshooting guide to follow. But we can create, you know, sort of different step-by-step guides or different sort of sets of instructions for lots of different things. Can you think of how a teacher might use a set of step-by-step instructions in the classroom?
In a classroom, in which context?
So maybe for something like science, if kids are going to be doing an experiment, you know, does the teacher just say, well, you know, go forth and experiment?
No, like in science, every science experiment has procedures. So in here, we are talking about the procedure. What do you do when you are going to perform a science experiment? Which things that you need, all those things. How are you going to kickstart your process of that experiment?
Okay.
Yes.
And there are a number of reasons for that. You know, it's dangerous to have children let loose in a lab just randomly, you know, mixing chemicals together. But also part of scientific thinking is about following a set process so that you're able to accurately record, you know, when you mixed, you know, this chemical with water, the solution turned blue or whatever. And you get certain results because you followed the instructions in a very specific way.
That is why we are saying it's computational thinking, because it is now identified. But it was all along there. Teachers were doing wonderful, fantastic job, and they were also guiding the learners through the procedure of doing things in the classroom.
Okay, for sure. So, Namusa, we've now talked about the 4 different types of computational thinking. Decomposition, pattern recognition, algorithmic thinking, and abstraction. That's it. And we've talked about how teachers can make computational thinking work in their contexts. How can teachers sort of get kids doing more activities that specifically develop computational thinking skills?
It's every topic in the classroom. You can apply it in every topic in the classroom. So in other words, when you present a topic in the classroom, make sure that you also introduce the computational thinking, that the learners will go through decomposition, will recognize pattern, will go through the abstraction. So it's all in one.
Okay.
Yeah.
So maybe it's just about a teacher not necessarily doing anything new, but when he or she is doing their lesson preparation, to be quite specific about, I'm going to use this as an opportunity to show my students the pattern and to help them identify it. Or in this activity, I'm going to, decompose a very complex sort of plot of a novel into smaller bite-sized chunks that will help them to understand it. If a teacher wants to specifically focus on computational thinking, there are also ways of including it sort of as part of sort of normal classroom practice. So I know my own child who's in grade 7, she gets a brain teaser every week. And the maths teacher will sort of set up a brain teaser and will send it home. But sometimes the things that are being asked aren't actually anything to do with what she's covering in maths that week. Do you think there's some value in giving kids something like a brain teaser of the week?
I think so. It makes them think not logically. Remember, most of the time when we teach kids to think logically. But how do you make them think not logically?
So think outside of the box.
So you create those activities that, yes, think outside the box.
And what I've found with my own child is as she gets more and more of these sort of quizzes or brain teasers to do, similar activities, come up from time to time, and she'll say, oh, this one's not that difficult. It's sort of like that one where, we had to work out which house Mr. whatever lived in based on a number of clues, which involved sort of eliminating sort of certain houses. Or sometimes it'll be an activity where it's a trial and error activity, and she's got to sort of try different numbers in the box until she gets the number that leads to the correct solution. But the more of these activities that she does, the more sort of ways of thinking she tries out. And even if she doesn't solve the brain teaser of the week, she's exercised her brain and had a go at thinking about it. And when the teacher sort of presents the solution in class or gets one of the learners to present their solution in class, you learn from that and you're better able to solve that sort of activity the next time.
Yeah, it creates that environment that the learner must not always just give up on something. You must try, and then you will get better next time.
Yeah,
I think that skill we really need from our kids.
And that's something that teachers, no matter whether they're teaching little ones or high school age learners, should aim to develop. Not giving up, trying something. And sometimes the solution doesn't jump straight out at you. I've encouraged my own child to try and sketch out the problem, draw little diagrams and sort of
mind mapping.
Yeah, and sort of see if that helps her thinking. Or to underline key words in the problem, which can also help. So that's something that my daughter does. But there's also something called the Olympiad Talent Search, which is a great resource for South African teachers. If they're looking for great computational thinking activities to try out with their learners, then this is a resource that they should definitely look at. Because this gets their learners to try different activities. They can enter them into the competition, or they can just download past papers and do those as these brain teaser activities, or the end of term, and you sort of are trying to sort of keep the kids busy for a couple of days. These are great activities for them. I just want to show our viewers where to find them online. If you go to olympiad.org.za and you look under Talent Search, and you go to read more, you'll see all about the talent search there. And if you go here where it says past papers, you can get past pen and paper activities that a teacher could print out and could then get the kids to answer. Or you can actually get online examples where the learners do the activities sort of on their sort of tablets or on their computers, but computers definitely aren't required. So sort of just as an example, here's one taken from the grade 5 talent search competition, and this one is called Worm, and it says a worm is sitting at the end of a branch on the tree shown below. It wants to eat all of the apples by moving through the tree's branches. The tree is made of 1 meter long branch sections. What's the shortest distance in meters that the worm has to crawl to eat all of the apples? Now, this looks pretty simple, but a child, particularly a child in grade 5, so that would be quite a young child, would really have to think. And maybe they would even sort of trace along with their finger or with their mouse. Okay, here's the worm moving 1 meter to the fork of the tree, 1 meter up to eat the apple, 1 meter back down, 1 meter down again. And they would need to know that the worm can't fly through the air. It actually needs to sort of crawl along the branch. And would sort of add up that, you know, if you go all the way along here and, you know, up there's no apple at the end of that branch, so that's not one worth going to. And they would work out, you know, the shortest route. I think the answer is 13, but maybe I'm wrong. And then they would get to the solution. But these are great activities for students to try and for teachers to use in their classrooms. It's an annual competition, and unfortunately the one for 2018 has already closed, but this competition's run every year. So if I was a teacher, I would get my learners to do a couple of past papers you know, between now and the end of this year, so that next year they would be ready for action.
Yeah.
You've got some of your
just
kids
to expose them as an awareness now, so that when it comes to 2019, they start entering the competition.
You've had some of your learners involved in other competitions in Mpumalanga.
Yes.
And what does this do for their sort of self-esteem, or, you know, do you find it boosts them? They take it more seriously because it's part of a big competition?
Yes, I have once observed the Astro Quiz that is conducted by the Department of Science and Technology together with the science centers in South Africa. So that one is the physical one. They are not going online. They come, they get, they are brief, they read about anything about astrology, and then they go, they answer some questions. So they are working in groups. So
Okay.
I think that's where the self-esteem comes in. So it builds the teams.
And working in groups is also a great way of doing this. And teachers who are letting their children work through some of these computational thinking past papers may very well want to pair sort of learners up or have them work in groups of 3 or 4 so that they can talk through their solutions. And, you know, sometimes if you have to explain to somebody else how you got to a solution, it really clarifies your thinking, and it means you can't just randomly guess for multiple choice. You've actually got to be able to explain, well, I did it like this because of this, this, and this.
And I hope maybe we can develop something that it will work with teams rather than a learner sitting alone at home doing the questions on the Olympiad.
Okay.
Yeah, teaming up with 4 in one team, I think it would be a good idea.
I think there are some team options available in the Olympiad competition. So I really do encourage teachers to check out that olympiad.org.za site and to see if there's something suitable there for your learners to enter, and do some of those past papers. Just to give a couple more examples of the types of things that people could expect, some questions related to computational thinking. This next one is a sample question from a grade 5 question paper, and it's all about a birdhouse. And it says a beaver wants to buy a birdhouse for her daughter's birthday. Her daughter says, I would like a birdhouse with 2 windows and a heart. The question is, which birdhouse should her mum buy? Click on the correct answer and it'll be saved automatically. So did the beaver mention, or did the beaver's daughter mention what colour birdhouse she'd like?
No, only 2 windows and 1 heart.
Oh, only 2 windows and a heart, right. So this is about abstraction. It's about focusing just on what the question is asking for. It's also a bit about pattern recognition. You know, the first house, it's got a heart and it's got a window, but they're the wrong numbers of hearts and windows. The second one's got the 2 windows right, but then it's got a star. And house number 3, that's the winner because it's got the 2 windows and the heart. So that's the one that meets all of the criteria. And if you were to make, you know, one of those algorithmic thinking flow charts for this problem, you could say, you know, does the birdhouse have 2 windows? Yes or no? If it has 2 windows, yes, it might be a contender. Then does it have a heart? No. Yes or no? And the first, you know, both of the first 2 birdhouses would fail, but the third one would pass. This next question is a little bit trickier because this one's taken from a grade 8 and 9 online question paper. This one's all about the dancing man, and it says Verity makes an animation of a man dancing. So far she's only completed the first and last frame. The man can only move one of his arms or legs at a time. There should be only one difference between film frames that are next to each other. Task is to drag and drop the images provided into the correct empty film frames below to complete the animation. And then you have to save your answer. So have you ever done flip book animation where you draw a series of pictures and as you flip the book, it looks like the little man does something?
Yes.
Or even if you take a series of photos and you move just one thing in each photo, you can then link up those photos and it looks like animation. So this is the same sort of activity, but the little man can only move one thing in the next frame because otherwise the animation won't work. So to make this, to solve this puzzle, you would need to look at which of the little red men in the strip at the bottom only moves one thing. And I think we would get all the way to the 4th little red man before we found one where only one thing was different. One of his arms is different, but the legs are the same and the one arm is still up in the air. So, so the 4th little red man would be the second one in the film frame, and so you'd go on to solve the puzzle. It looks quite easy, and actually it is, but it actually requires quite a lot of thinking and looking at a pattern very closely to look for which of the men shows only one difference.
Yes.
I don't know if I could have solved something like that so easily in grade 8 or 9, but you also build these skills by doing, you know, more and more of these activities. So there's one more example, again taken from the Computer Olympiad, and this is also from a grade 8 and 9 question paper. This one is from a pen and paper question paper, whereas the other 2 we looked at were ones that somebody could do online. This is all about a car trip, and a self-driving car needs to take Beaver to school. The car is programmed so that it only uses 3 instructions. Forward, go forward until you cannot go forward anymore. Turn 90 degrees left, turn 90 degrees right. And the question is to write us which set of instructions or program will get the beaver to his school. And then it's not showing on the screen, but there was a series of different examples that the learner would have to choose from. For this, what type of computational thinking would this one involve?
I think it's the sequence, flowchart.
Yeah, exactly. It
Yes.
involves coming up with an algorithm, because you can't just get the beaver to turn at the first street that it sees, because that's not an option with this self-driving car. With this self-driving car, you can only turn when you get to the end of the road.
Yes.
So the beaver wouldn't necessarily take the most direct route, but it would take the shortest route that was available with the 3 types of instructions that it can follow. So from these examples, I'm hoping teachers realize that computational thinking is not that difficult. But it's a bit like exercise. You know, the more you sort of move your brain and think in different ways, the easier it becomes to start structuring your thinking, breaking things down, following a structured or routine order. And it does get easier over time.
And it's also relevant to the teachers themselves when they prepare for something. You know, when you prepare for your presentation, you know, you want to move from one point to another, and then how do you make sure that everything that you want is packed in that presentation, so that you don't leave other things that are important outside.
For sure, and also that your presentation is structured in a logical, orderly way, not you jumping from thing to thing as it occurs to you, but that you start maybe with a global view, and then you sort of explain the bits step by step, and then maybe round off by sort of talking about the whole again. Namusa, if somebody wanted to find out more about computational thinking, is there a course they could try?
Yes, there is a course on Microsoft Educator Community Portal. The educators must go there. In fact, in Mpumalanga, I'll be presenting the portal to the teachers. These days, I'm presenting that. I'm getting them to work online.
Well, that's great, because then teachers can, do the courses that most interest them, that are best for their needs.
Yes.
And it's also great that teachers can earn points and earn badges for the different courses that they've taken.
Yes, I'm packaging all my presentation about the benefits of being in that portal in terms of their professional development. So that will be a great workshops that I'll be conducting.
Okay.
Yes.
Well, we'll definitely look out for those.
Yes. After that, I'm definitely sure that on their own, they will, at their own spare time, they are having smartphones, they are connected to the internet, they will go to that portal.
Yeah. Anywhere, anytime learning. That's what we want to see.
Yes.
So Namusa, that brings us to the end of this session on computational thinking. Are there any final bits of advice that you'd like to give to teachers?
Like I'm saying, teachers, we need to get fast. We are moving at a very slow pace, but I'm thinking we are getting there. We need to familiarize ourselves with the Microsoft Educator Community Portal. I'll be helping you at any time if you want me.
That's great, Namusa, and thank you so much for sharing your experiences and your knowledge with us here today. I think if teachers want to teach computational thinking, they need to be computational thinkers themselves. Think through your thought processes, plan your lessons in an orderly and structured way, and aim to include aspects of computational thinking no matter what subject you teach or to what age level. Please look out for our next Microsoft Virtual Academy, where we'll be talking about other computer science terms and technologies that you can bring into your classroom. I'll see you then. Goodbye.
Bye-bye.